Okay, now let's begin the process of converting our 1D solver quickly to the 2D solver, and this will be a simple process. Let's do this as fast as possible. So some of the stuff is just a grind, so we'll just do it quickly. So this is now the 2D mesh reader, and so there will be no excluded flags. That is for the next test case. So this should be X, so we are reading the nodes for X and Y. This is your node to element connectivity list. This shouldn't change. So for the Gauss rule, we are using the 6-point Gauss rule, so I have just written it down here. Let me just copy it. So here you can see that there are two columns here. So the first column is for Xi and the second column is for eta. So because in the previous case we were using 1D, so here we just need for 2D we need Xi and eta as well, two values. Okay, and these are your Gauss weights. So this is pretty much the same, and so let's measure the number of nodes, and the stiffness matrix will still be the same. We'll just initialize it. So the same, the total number of nodes will be the rows as well as the columns. So for the force vector or load vector, the total number of rows will be your n nodes and one column. So really the change is going to happen in the isoparametric mapping and in the shape functions. So let's just define our shape functions. So if you remember, we have already derived those, so these guys are really easy. So here we just have two derivatives, so d and d eta, and this will be eta. Okay, and these shape functions will be 1 minus xi minus eta, xi and eta, and these guys, so they will just be piecewise constants. So minus 1, 1, 0, right? dn d eta is equal to minus 1, 0, 1. Alright, so this is simply our shape function library, very simple for the linear case. So for the isoparametric mapping, this will be slightly more complicated. So we don't need any radius here. So our weak form will just have the physical derivatives in the x and y direction. So let me just define this as the physical derivative, or I should rather, yeah, dn dx physical and dn dy physical. So in the 1D case, we calculated the physical derivative here, that is dn is equal to, so we use the chain rule. So in this case, let's just get the physical derivatives out in the helper function itself. So instead of length, we have determinant of j here. Okay. So we need the element value, the elemental nodal values of x and y coordinates, and we need dn dxi. We don't need n because there is no interpolation for n required here. So in the previous case, we were using spherical coordinates, so we needed to calculate the value of r, and we required n just for that purpose. All right, so let's revisit the formula for j. So this was our matrix, so let's just build this dx by dxi, dy by dxi. So let's just write this down first. We really have to be careful that we don't flip anything or transpose anything, so any small mistake is possible. Okay, all right, I I think that's correct. So I just have to now evaluate these guys. So I can just do it using the x and y values. So dx dxi will be xe into your derivative shape function evaluated at the Gauss point, and the same for this guy as well. And now let's just do it for eta. Alright, I guess this is correct. Alright, okay, so now let me define the determinant. So dx dxi into dy d eta minus dy dxi into dx d eta. Alright, and now we have to take the inverse of this. So let us say inverse of j is inverse. And now let's define our physical derivatives. J1 comma 1 to dn dxi plus j1 comma 2 into dn, right, oh, dn d eta. Alright, and now let's just do the second one. So this will simply, we just have to replace these guys by 2. Okay, so this is our helper function, and so now we have done the isoparametric mapping. Alright, so I made a mistake here. So this is just inverse. Okay, so let's start off by using a Dirichlet boundary condition. Let's say phi outer is equal to 0, and then we'll impose a Robin boundary condition. Okay, so now we just have to make the changes in the element matrix, and here really this is simple, and we just have to make this Gauss rule equal to 6. These guys have to become these are our elemental y coordinates, and this will remain the same. So previously this was for quadratics, but even in case of triangles we just have 3 points, so this will remain the same. Okay, so now let's just call our helper functions. Let's just paste them here. You have g point of g, g comma 1. So this is our psi column, and then just add the eta column as well. So this will simply be 2. And now let's do the isoparametric mapping, and so now we have our physical derivatives. We can also just rename them simply as dn dx. Okay. Alright, so dn dx into dn dx transpose. So this is the first outer product in the x direction. So for our second order derivative in the x direction, and this is the y direction. Let's remove the radius term, and this will be determinant of j, and I think everything else should be the same. So now we just have to apply our boundary conditions, and for this we can just write a for loop. So there are other easier ways of doing this, but I'm just going to use a for loop here. So this is our inner node, and so these are our outer nodes. So right, so now this is a line boundary, right? So I just use nodes here, and let's rather use the easier version. So we can do a for loop, but I think that will just be time consuming. So I think we already know what we have to do. We just have to zero out the row, and then we simply have to put the diagonal element as 1. Okay, so let me just use this instead of the for loop. I think I just missed this. Okay, right, and we are still using a directlet condition. So let's just Alright, so now this is our application of boundary conditions. We could write a for loop, but I've just skipped that for the time constraint. So this won't be our solution anymore. So, and we'll need a scatter plot. So let's use this. So this is a good way to do a scatter plot. Really, MATLAB is not really good at doing these unstructured plots. So we are better off with paraview for that, but in this course we really don't need paraview because we just want to understand the coding. And okay, oh, I did not remove this. Right, so this is our solution, and you can see we have a 50 directlet here, and at the boundary we have a 0 condition. So this is our smooth, very simple diffusion solution. So now let's apply the Robin boundary condition. So for this we just have to remove this guy, and let's just write a Robin loop. So let me just call this as a Robin loop. And so I'm really going to simplify this for the case of linears, and I can do this for linear elements, but for the actual case, so this is just a boundary integral. And so for a boundary integral, again you should do the isoparametric mapping, and again you should have a shape function library, the exact same thing, but I'm not really going to do that. So I'm just going to use so really in the isoparametric mapping I just need det j, or the scaling factor, which is the length. And if I was using quadratics, which are curved elements, or cubics, so which can really hug the boundary and be curved, so for that, to calculate the correct length, I'm better off by doing the isoparametric mapping. But since I'm using linear elements, I will just calculate the length directly from the x and y coordinates. So so let me just start off by, so flag 4, right, and let's use our 1D Gauss points. And now let's just run a for loop. So we already have the node to element connectivity list. So this is simply your boundary info.flag4. So these guys, right? So this is your element to node connectivity list. So we can just parse this list, and now let's just define the two nodes. So I'm sure there's an easy way of doing this, but let me just do the grind here. So I think doing it like this will also make it a bit clear. So we are just getting the x coordinates of these two nodes and the y coordinates. So I think I should have just gone for the isoparametric mapping. This is a bit long drawn, but okay, so we are near the end. x1 minus x2 the whole square plus y1 minus y2 whole square. Right, so this is my length, and so now let me define a local level matrix for my boundaries. So I'm calling it MR, which is analogous to like mass matrix for Robin. So sometimes in literature you might find a mass matrix for Robin. So that is probably because we are not having any stiffness matrix like derivative terms here. I'm not really sure, but I am just using the mass matrix kind of notation here because I just have a mass matrix like term here. So in the mass matrix which we use for the time derivatives, we really have just the multiplication of the shape functions, and there are no derivatives. So we really have something very similar here. Let's define a helper function again. So function shape lin b at xi, right? Or maybe I can just call it xi at the boundary. So these are your shape functions at the boundary, your linear shape functions. Okay, so this is our helper function. So now let's just call this. And now we can just accumulate the integral. So let's look at the boundary term. So this is phi by r, and r is the r outer 12. So in this case, this is just your xy coordinate. So we'll just plug this in directly. There is no multiplication with r because in the weak form we just get the d phi by dx, right? So alright, so let's just plug in 1 upon r outer into your mass matrix like structure, right, into L into your dose weight of G. Right, so this should do it. This will accumulate the the integral, which is the boundary integral. Now we have to add it to the element. So let's just define these two nodes. These are our boundary nodes, and then at boundary nodes comma boundary nodes, we just add this. And okay, so I think this is our Robin loop and this is ready. So let's just solve this now. There's probably some issue here. Yes, there's some issue. I think I did not multiply the Gauss weights by 0.5. Yes, that's right. So this is the solution where you get almost 14.3 at the outlet. So you can just derive this analytically, and we will also look at the flux at the boundary. So in the next, so this is our solution, and you can just compute analytically the flux at the boundary. And so this flux has to be around 90. And in the next lecture, we'll just begin with doing this integration. And you can even verify this 14.3 analytically, so it will come very close to this value. So I'm not showing the actual derivation here, so you can just solve this problem on paper, and you should get this value. And the flux at the boundary you should get as 90, and we'll just compute it in the next session, and then we simply have to shift to the other geometry in which you have these two circles, and we'll just calculate the flux again at these two circles. Okay, so that's about it. And you could see that it is very easy to go from 1D to 2D, and this was without any hiccups, I suppose. We just struggled a bit at the Robin loop, and it's just a bit more tedious because you just have to keep on doing the integrations, and that is so that's the difference between finite differences and finite elements. So in finite elements you will have to do the integration everywhere, so you will have to have the Gauss points, and you will have to ensure that the integration is with the correct number of Gauss points. You can't even add very high number of Gauss points, or else your solver will just stall. It will, because your Gauss points are the innermost loop, and if you blow this up, then you will really get very slow kind of performance. So I hope this was helpful, and now in the next session, let's just quickly go to the next problem, and also use the reaction forces for computing the fluxes at the boundaries. And after doing this, we'll be able to go to the 3D problem, and that would be the end of the main part of this series. And after that we can just have the extra session where we'll just do all of this in Phoenix, and we'll just confirm all of these results. So the boundary flux as 90, or in case of the next problem, the analytical solution will give you I think it is 137. So all of those values I will just provide you, and we'll also confirm it in Phoenix once again. And so I have already done that, of course, but I'll just do it again in front of you, and you will basically see that the workflow of Phoenix is very easy, and it's very intuitive. So it will be a lot of fun. And after that, then we can go to the next course where we can do the 2D Navier-Stokes coding, or even 3D Navier-Stokes coding. We look at turbulent flow and some really interesting problems. We look at SUPG upwinding. Maybe we can solve the flow past a cylinder, those kind of problems. So now with this 2D solver, you can see that we have really unlocked a lot of potential. So we can now feed in lots of different Gmesh meshes, and the workflow to 3D will be really simple. So I don't think I'll just live code it, because the live coding sessions are really long. So I don't want to bore you, so we'll just really the workflow is very simple for 3D. Once you have done the 2D case, so the Jacobian will just become bigger, the shape function library will change, and in this Robin loop you just have more bookkeeping, because instead of line integral, this is surface integral, 2D integral, and your Gauss point, your Gauss rule will change, and for a tetrahedron this will also change, right? You will just get another term here in the Laplacian, but you will again have determinant of j here. So the structure will be really similar, so it's very intuitive. Again, for read mesh file, for the boundaries you will have triangles, and instead of and for the elements you will have tetrahedrons, so you will have tets in that case. So I hope this was helpful, and let's just conclude here, and in the next session let's just wrap up with the 2D problem. Thank you.